we'll talk about those briefly and then continue. But to finish up, we've got to get into two major concepts. One is proofs, which we will do in every unit for the next 4 units, I think. And this is starting that. And then also angles formed by parallel lines with what we call a transversal. And so look for we'll have a quiz on that stuff probably end of next week, potentially. Anyway, it's interesting. I think the proof stuff can be a little weird at first, but then you get the hang of it, and it trains your brain how to think through a logical argument, which is really important. And then the parallel line stuff it's kind of like a puzzle, I think. That's how I think of it. So let's put a couple of these things in your notes. And before we do that, inductive reasoning is a big part of proving. It's really a part of everyday life for most people. So it says it's a type of reasoning that reaches conclusions based on a pattern of specific examples of past events. So clearly the ones here, like these two, are just numbers, but I'll explain how you have used that in your life. So in terms of this first one, you're looking at a pattern of past events in the sense that there's a series of numbers, and you're trying to predict the next couple numbers in the sequence, which is what comes after 64. What was it? Okay, so 58 and what? Okay, so we get the idea that this is going down 2 each time. Good. Now, could you be wrong? Yeah, I mean, potentially when we make observations of past events, our inductive reasoning yields a wrong conclusion. But it doesn't mean it's wrong, but it could be. Usually it does pretty good, though. Like, for example, in this next one, 3, 5, 9, 15, 23. What do you think that's? What was it? Okay, 33. 46, you said? Okay, so describe the pattern in that case.
The first one is adding 2, and that's doubling how much it adds every time.
Okay. Adding 2 every time? Yeah. Good. So it's adding successive even numbers, we could maybe say, right? And again, you saw that based on past events, which is the numbers that we saw sitting there. Cool. So you just used inductive reasoning to do that. Now let's broaden this a little bit to something beyond just numbers and patterns. How many of you have observed things in your life, like outside of the classroom, and drawn conclusions from that? Anybody? You might have done that today, honestly. But think of something that, hey, I've seen this happen 3 or 4 times. I bet that you see a pattern. I bet that means that this is true. Anybody think of anything like that? We actually do this fairly often as people. Raise your hand if you've ever gone to Starbucks. Okay, I mean, most people have. So if you've gone repeatedly, you start building up a pattern of understanding that Starbucks is worth it, it tastes good, and it makes you happy, right? And so you draw this conclusion, okay, Starbucks is a good thing. I enjoy it. It's worth my money. That's inductive reasoning applied to life. Could you go the other way? Like some people say Taco Bell makes them sick. Has anybody ever had that experience before? Okay, I'm getting some nods. So same idea. Like I've heard people tell me I don't eat at Taco Bell. Well, it's because they're using inductive reasoning to say, I've eaten there. I see a pattern of eating there causing me to feel bad. Therefore, I draw the conclusion that Taco Bell makes me sick or something. Okay? Or whatever. Substitute your opinion in there. When I look outside in August and I see sun, I know it's hot. Right? If I look outside in December or January and I see sun, I know it's cold. That's inductive reasoning. Like you're seeing a pattern that leads to a conclusion. So we use this obviously in life a lot, but also in math. The conclusion that we're drawing, the part that we say, hey, I think this is true, that's called a conjecture. So when we said 58, 52 in this first number pattern, we were making a conjecture that we were decreasing, and I didn't write this, but decreasing by 6 each time. That is a conjecture. Like I said, it could be wrong. It isn't in this case, but that's a conjecture. It's an unproven statement. So we might have to end up proving that. And that's going to be part of our work coming up. Did anybody do the dot pattern one? Okay. So if you look, we're adding 1. So I'll just fill in this first one. We're adding 1 to each row, and then we're adding a row each time. So that's how we go from the first one to the second one to the third. We go add 1 to the row and add a row. So that's our pattern. That's our conjecture. So what would this last one be? Okay, it would be, in the sequence, it would be number 5, like box 5 or pattern 5. Okay, and it would have 6 dots along the bottom. And it would add an extra row to have 5 rows. So it would be 30 total dots. Okay? Now I didn't draw it the same size, but it's the right number of dots. So that's a conjecture. Okay? Do you feel like you've done this before? Not just mathematically, but like with life, like maybe even today. Okay? There are some days when I drive in and it just seems like people are impatient or people are like crazy. And after seeing 2 or 3 drivers that are driving that way, I start to make a conjecture that there's something in the air or whatever. It's just a weird day. Okay? Let's go write a few of these vocab words down in your notes. As a group of concepts, this is called logical reasoning. And it's definitely not a specifically math concept. Like I said, we use this just to function in life. So the first one is inductive reasoning. So we're drawing a conclusion by observing patterns in past events. This is specific to general, meaning we're observing specific cases and making general conclusions about it. Conjecture. This is not just a math word. You'll hear this if you talk to anybody about their opinion. Like if you're talking to an educated person that maybe you're debating about opinion, and you might hear someone say, oh, that's just conjecture. Meaning that's just a conclusion you've drawn. It's not necessarily fact. Let's make sure we put an unproven, if I could write, unproven conclusion drawn from inductive. And we're going to mention this in a second, but we also have deductive reasoning. It's an important word to know. Someday somebody might tell you that you're just giving conjecture, and you might have to back that up with fact to prove that what you're talking about is true to them. Okay. I'm going to show you, just stay there on your notes. I'm going to show you a graphic real quick to compare and contrast these two types of reasoning. So we just talked about inductive reasoning, which is observing a specific occurrence or multiple. Like we just saw with the numbers, we observed like 5 different numbers, but they were specific numbers. We saw a pattern. We kind of thought, hey, that looks like it's decreasing by 6. So we made a conjecture that that was true, okay? Sometimes you can think of a conjecture, actually not, stereotypes are often conjectures that are unproven, but it's based on repeated observation, okay? So whether or not a stereotype is true, it typically results from inductive reasoning and observation. Okay, that stands in contrast to deductive reasoning. Notice it's the exact opposite. We take some general theory and we work down and apply it to a specific instance. Okay? So basically the opposite process. So we have the general theory of gravity. Like we know that that exists, and so anything that has mass we can apply and say, oh, that has gravity. Like we can look at a planet out in space and say we know it has gravity because it has mass. We don't have to go there and observe specifically that it has gravity. Okay, that's just a kind of a big idea example. Seatbelts save lives. Could that be a deductive reasoning? Yeah, like that's a theory, right? That's a generally accepted truth that everybody agrees upon. Seatbelts save lives. So when you get in the car and buckle up, you're applying your deductive reasoning to, hey, I know seatbelts save lives. I'm going to apply it to my specific case and hopefully save my life if needed. Okay? So we use these all the time. We don't talk about their names, but our brains are created to use deductive and inductive reasoning every day. That's how we function. Draw conclusions. So this is applying a general truth or theory to a specific case. We will use both in our proofs. We're not going to specifically call out that we're doing this. We're not going to say this is inductive reasoning or deductive, but we will be using both of these. Often these are written, and we've actually already seen some of them, but often these conjectures are written as what we call conditional statements. And these are worded this way. The general structure, now we can manipulate them a little bit, but in general, if something, then something is called a conditional. And this has 2 parts. This part that follows the if is called the hypothesis. The part that follows the then is called the conclusion. Hypothesis is the condition. The condition that must be met. The conclusion is the result of the condition being met. So, you've all heard this for sure. Lots and lots in your life. Parents are famous for using conditionals. Give me an example. If you then you. What could you fill in the blanks with that? If you okay. If you be good, then you can go to the mall or whatever, go hang out with your friends, then you can borrow the car. It's always things like that, right? If you mow the yard, then you can watch a movie or something. I mean, it should be that way, honestly. We have these in math too. So I'm going to go show you some. I just want to make sure everybody's got it. Looks like we're pretty close. So here's some. Here we go. Here's an example. It's not worded in the if-then, but it's there. Alberto can go to the movies if he washes the car. So what's the hypothesis of that conditional statement? Yeah, he's got to wash the car. The condition that must be met is that he has to wash the car. If he does that, then he can go to the movies, okay? Here's one we all understand. You can register to vote if you're at least 18 years old. So hypothesis, you got to be 18. That's the condition that must be met. If that is met, then you can vote. Okay, in math, we've had these. So, like, in terms of some of our theorems, tell me about, let's just do a quick review. If I have a triangle, what is true about those three angles in the triangle? Yeah, so it said something like if, let's do this, if the figure is a triangle, I'm going to just draw a triangle for that, then the angles add to 180. So that is a typical wording of a theorem is in conditional form. If this condition is met, then this conclusion can be drawn. If we have a triangle, then all the angles add up to 180. Okay? We had the segment addition postulate. If points are collinear, then the segments add up to the total, like that kind of thing, right? What does collinear mean? On the same line. What does congruent mean? Yeah. Okay, let's talk about this word. Counterexample. It shows that a statement or conjecture is false. That's a big deal. If I can give a counterexample, it kind of disproves this conjecture, right? Or this conditional. So think about, it said if Alberto, if he cleans the car. So if he washes the car, Alberto can go to the movies. What would be a counterexample to that?
If he doesn't wash the car,
Yeah, well, and we don't have to necessarily say the second part, but a counterexample is a dirty car, right? That disproves the fact that he did the job. Okay? Let's do another counterexample. Let me get a blank part here before this. So I'll write a conjecture. How about this? If you know band, and we're going to see one like this in a second, but if you know band instruments, all brass instruments are trumpets. Is that true? So what's a counterexample? Counter meaning against. So an example that's against this statement. Anybody? How many of you played in a band before? Okay, usually a lot of people do, in middle school. So Nathan, what's a counterexample for this? What's something that disproves my conclusion that all brass instruments are trumpets? Aldo, how about you? Like for real, you don't know? Okay. Mason? Ezekiel? Trombone, yeah. So the trombone is the kind that slides, has the big slider like this. It's brass, but it is not obviously a trumpet. Okay, let's do another one. Let's get this concept kind of locked in. I don't know if this is a good one, but... And we don't always have to say all, but it kind of makes the counterexample process easier to think through. Here's an easy one. All summer days are hot. What's a good counterexample for that? Okay. Yep. So maybe a cloudy day. What else? We're still technically in summer, even though it's September. Like by actual counting, we're in summer. And Saturday morning at our house, it was 46 degrees. Is that hot? Okay. So a 46-degree morning. Actually, that was Sunday morning. That's not hot. My wife and I lived in Fort Collins for a while, and one 4th of July, it was like 50 degrees, no joke. It hailed, and this big storm came in, and it was cold. It was pretty chilly. Okay? So 50-degree 4th of July. So these are specific examples that disprove my conclusion that all summer days are hot. Okay? We should probably write counterexample in the note real quick. Write it in here with conjecture. Would be the best place to put it. So this is a specific example that disproves a conjecture. All right, one more thing to write. Guys, make sure you have your devices turned off, not just put away. All right. So here's another brass one. The converse. We'll talk about what that is, but here's a conditional. So we just talked about what that is. We also talked about a counter example for it. So if you play a trumpet, then you play a brass instrument. This got cut off, but it's instrument. Okay, we already talked about the fact that a trombone is a brass instrument that is not a trumpet. So, but first of all, is the statement given true? If you play a trumpet, then you play a brass. Is that true? Okay, so yes, this is true. When we write a converse, and coming up, we're going to depend on these converse statements pretty heavily, like probably tomorrow or Wednesday. Actually, it'll be Wednesday. All we do is reverse the two pieces. So this says if you play a trumpet. That is the hypothesis of this statement. So it's the condition that must be met. And then the second part is the conclusion. That's what happens if you meet it. All we do is reverse those for a conditional. So how would this sound if we reverse them? In other words, write the conclusion, the original conclusion now becomes our hypothesis. So if what?
If you play a brass instrument, play a trumpet.
There you go. If you play a brass, I'm just going to leave it that way, then you play a trumpet. Okay, so we just switched it. We just reversed it. What?
So Congress just means like if you swapped it and then that's what Congress means?
Yes, that is what it means. I want to go back though to this one. So yes, we flip-flop, but we have to know what the hypothesis and conclusion are first. So let's try it on this one. Because we don't want to just flip-flop the order if it's the wrong order to start with. Does that make sense? So in this one, we said, which one is the hypothesis? This part is the hypothesis. And then the conclusion was that you can vote. So how would we rewrite this for the converse?
If you're 18, register to vote.
That's what it already says. See what I mean? So we have to be careful. So we switch the order of the conclusion and hypothesis. So the converse, let's see, I'll write it up here. Converse. If you what? So now the original conclusion has to be the new hypothesis. So the original conclusion was that you can vote. So now that's our new hypothesis. So if you, help me out. There you go. If you are registered to vote, then what? Then you are at least 18. Okay? So does that kind of help?
Yeah.
And let's just analyze the truth of this one. Is the converse true of this? Yeah, so see how this case, they're true both ways. The original and the converse is true. But the brass one, if you play a brass, then you play a trumpet. That is false. Because we already had the counter example, which was the trombone. So counter example was the trombone. Okay, so let's go put converse on here. That'll be the last thing that we put. So we'll kind of describe, we're going to rewrite the original conditional. By reversing the hypothesis and conclusion. Let's actually just do an example, okay? So originally our hypothesis will be if what? How about this? If it is raining, then it is cloudy. Actually, let me change color on that second piece. Okay. So I'm going to probably use 2 boxes for this. So this is our hypothesis in the original, and this is our conclusion. So now we switch those, and this will be our converse. How will it sound?
If it's cloudy,
Yeah, good. So it is important to identify which, like the hypothesis and conclusion, because the order matters when you go to converse this. Now, like I said, this is a really big idea, this idea of converse. It will allow us to prove that 2 lines are parallel. It will allow us to prove that something is a parallelogram or square or those kind of things. So, kind of a big deal. Was the converse true in this case? If it is cloudy, then it is raining? No, that's not a true statement. And what would be a good counterexample for that? I'm just going to put an example of that. We have this a lot here in Grand Junction. So what's a good counterexample? What is a specific example that disproves that statement that we just wrote? Yeah, just a cloudy day with no rain, right? Which, like I said, that happens fairly often here in Grand Junction. So all of these concepts are going to be ones that we use to prove things. And then, so here's what I need for you tonight. I want you to come up with an inductive reasoning conjecture from your day today. Like, I observed this specifically, and I want like a generalized conclusion from that. And then write a conditional statement and a counterexample to that. A conditional, converse, and a counterexample. I'll put it in the post, but please just write that down for discussion tomorrow. And we'll pick up with that. Remember, you're going to advisory now.